show up to these lectures on Teams. It's great. I appreciate that, and I'm sure you guys like having a class during class time. It's very nice. So let's start talking about what's known as atomic number, mass number, and isotopes. So let's do that. Well, atomic number, we use the symbol, the letter Z, to represent atomic number. And atomic number is nothing more than the number of protons in a nucleus. I'm even going to get ahead a little bit here, and I'll just tell you something. Look deep into my eyes and I'll hypnotize you and tell you that what governs the identity of an atom is governs the identity of an atom, of an element, is the number of protons. It's not the number of electrons, it's not the number of neutrons, it's simply the number of protons, nothing else, okay? So the number of protons is very important. Now the mass number is the symbol A, and that is equal to the number of protons plus the number of neutrons. So another way of expressing that, since atomic number is the number of protons, you could also say, well, mass number is equal to the atomic number plus the number of neutrons. Either way is perfectly fine. Now, isotopes, and I'm sure that some of you have heard of isotopes before, but if you haven't, isotopes are just atoms of the same element. So what does it mean? They're all going to have the same number of protons, but they have different numbers of what? Different numbers of neutrons in their nuclei. So if we change the number of neutrons, but the number of protons remains the same, it's still the same element. So the way that we represent an elemental symbol is as shown here. Now I'm going to draw it maybe a little bit bigger here. So we have X for our elemental symbol, and then A at the top, that's our mass number shown here, and the letter Z at the bottom, that's our atomic number. And so there are 3 isotopes of hydrogen. In fact, we could write that here, 3 isotopes of hydrogen, okay? Now, again, you can see that they all have the same atomic number. What do you mean, Mr. Dion? Look, they all have the number 1 down here. That means they all have 1 proton. So they're all the same element, right? They're all hydrogen, but they're different isotopes. Why? Because their mass numbers are different, right? This one has no neutrons because 1 plus 0 gives you 1. This one here has 1 neutron because 1 plus 1 gives you 2. And this one here must have 2 neutrons. In fact, we could even scribble that in here. We have 1 neutron in here, and we have 2 neutrons in here. Now, there's a few ways you can express these, okay? So this one is simply called hydrogen. This one here, you've got 2 options. You can either call it, and I'm not going to scribble it down because it's in the textbook. You could either call it hydrogen 2, or you could call it deuterium. So that letter D, that stands for deuterium. Okay, now the other elements don't have these sassy names for their isotopes. Only hydrogen does. Now hydrogen 3, which is the next one, okay, we can either call it hydrogen 3, okay, hydrogen 3, or we use the letter T, and that represents the new word, which is tritium. Okay, now remember, the chemical properties of these isotopes are going to be the same. And if you're like, well, what about atomic bombs, Mr. Dion? I heard that has something to do with isotopes. That's nuclear chemistry. That's not what we're talking about right now. Okay, I'm just talking about regular chemical reactions that don't involve, manipulating nuclei in any way. Okay, so here we have 2 other isotopes down here at the bottom. I'll just point out to you that they both have the same atomic number, right? They both have 92 protons. What's different is the number of neutrons. You can see that in this one on the left, this is uranium-235. Can anybody tell me how many neutrons there would be in uranium-235? I'll write down here, protons is equal to 92. Who could tell me how many neutrons there would be in uranium-235? Not a trick question. Yeah, Tyler says 143, and so does Reagan. Yes, exactly. It's going to be equal to 235 subtract 92, which is equal to 143. Now, there's no charge in this element, too, and so it's going to have 92 electrons because we have to balance out the charge of the protons. So we would call this uranium uranium. That's not very neat, is it? Uranium 235. Okay, over here we have uranium 238. It still has 92 protons. How many neutrons does it have? Well, it's going to have 3 more. It's going to have a total of 146 neutrons. Now, if you're confused and if you're like, where did you get that number from, Mr. Dion? I used this formula right here. Okay? I have the mass number and I have the number of protons, and therefore I can solve for the number of neutrons. And the number of electrons in uranium-238, there's no charge indicated, so it must be 92 electrons. All right, here's just a picture depiction of the isotopes of hydrogen. So we have hydrogen 1, hydrogen 1. Oops, I didn't mean to do that. I meant to do this. Copy. Come on, paste. Would have been faster just to write it, okay? We have hydrogen 1, we have hydrogen 2, and then we have hydrogen 3, okay? And again, you can call this deuterium. You can call this tritium. Okay, and you can see the difference in the nuclei. They all have what? They all have 1 proton, 1 red dot in the middle, but the number of neutrons differs between them. So that's what isotopes are. All right, let's take a look at a sample problem. We'll go through this one kind of quickly because we just solved something almost identical to this. It says here, give the number of protons, the number of neutrons, so we'll use P, we'll use P for protons, the number of neutrons, and the number of electrons in each of the following species. So in sodium 20, the atomic number is 11, so that means we have 11 protons, but the mass number is 20. So 11 plus what gives you 20? Well, it's 11 plus 9, and so we know that we have 9 neutrons. There is no charge indicated on this isotope of sodium, and so we know that we must have the same number of electrons as we do protons, and so the number of electrons is going to be 11. I'm going to skip the next one because it's virtually the same exercise. I want to skip ahead to C, okay? Can anybody tell me how many protons there would be in oxygen 17? This might be a stretch, but I'll give it a shot. Yeah, Reagan says there's 8, and Reagan is correct. So where did you get that number from? Looking at the periodic table. So if you have a periodic table, it's always a good idea to have a periodic table at your disposal when you're in chemistry class. You can print one off the internet. I have one posted to Canvas, or sorry, D2L. And if you take a look at that, you'll see the atomic number of oxygen. It is the 8th element in the periodic table. And so we could put the number 8 here. And so oxygen always has 8 protons. The number of neutrons must be 9, and the number of electrons must be 8 to balance that out. Carbon 14, the same kind of exercise. I have to go to the periodic table, and I see that carbon is element number 6 on the periodic table. And so I could put carbon has an atomic number of 6, and it has a mass number of 14, or this isotope of carbon does. And so carbon always has 6 protons. 6 plus 8 gives me 14, so it has 8 neutrons, and it has 6 electrons. All right, that's a pretty simple example. Now let's move ahead and talk about the periodic table. This would be a lot more fun if we were in person, but I'll kind of give you my 2 cents about the periodic table. Is that chemists had discovered several or many elements, a long time ago, even in the Middle Ages. They knew about things like copper and gold and oxygen and so on and so forth. But what's happened is that chemists knew that several elements had characteristics or reactivities or behaviors that were similar. And they noticed that there was kind of a repeating pattern with the elements when they are arranged a certain way. And the first person to arrange the elements in something that is close to our modern periodic table was Dmitry Mendeleev, who was a Russian scientist. And what he did is that he made playing cards for each one of the elements that he knew. And he would lay them out on the table, and and he was trying to find all kinds of ways to organize them. Now, if you really want to get into the history of the periodic table, you can see that there was all kinds of crazy, I shouldn't say crazy, there was all kinds of interesting things that were postulated in terms of ways to organize the elements. I'll tell you one is that a scientist named John Newlands proposed that he thought, well, they kind of repeat every eight atoms. There's kind of some repetition here. And so he came up with what was called the law of octaves, which is similar to the notes in the musical scale. So he proposed that elements actually mimic musical notes. Now, we know that's not true. Back to Mendeleev, what he did is he was able to lay the cards down and come up with a precursor to our modern periodic table. And what's so remarkable about what Mendeleev did is that he was actually able to predict elements that hadn't even been discovered yet. For example, he knew about aluminum. Aluminum is element number 13. I have it circled here in yellow, but element number 31, which is gallium, which is just below it, had not been discovered yet. And he proposed an element and he called it Eka aluminum, EKA-aluminum, I believe is how he named it. And without gallium even being discovered, he was able to predict its reactivity, its boiling point, its melting point, its appearance, just by virtue of the fact that there is a repetition in the periodic table, right? What does period mean? It means that there's something repeating over and over and over. And so when you organize, or when the elements are organized in the periodic table, you can see that we have these blocks here. And if you look at a horizontal row here like this, we call that a period. So we call a horizontal row a period, and we call a vertical column like this, we call that a group, okay? And sometimes the groups, now this is something I've learned since moving to the States, but sometimes people down here, they call the groups, they call them the families. And what do you know about people in families? People in families will resemble each other, right? And so if you look at the elements that are in families, for example, if you look at the first family, that kind of sounds like a royalty thing, right? But if you look at the first family in the periodic table here, the alkali metals, those elements in that group or that family share a lot of characteristics, and we'll talk about what those are. You can see that the next group is the alkaline earth. In fact, that is spelled incorrectly. It should be, I'm going to have to twist my iPad here, but that should be spelled the alkaline earth. So alkaline with an NE on the end. The alkaline earths, they share many properties. You should know the name of the first group and know that it is the alkali metals. You should know the name of the second group, which is the alkali earths. You should also know the names of the last two families or groups. You should know the halogens and the noble gases, and we'll talk about those even more. And if I don't, of course, they're covered in the textbook. Some other things I want to point out about this periodic table is you see there are some interesting and beautiful colors here. You see that most of the elements are in fact colored green. And the reason why is because that color represents metals, and most of the elements in the periodic table are actually metals. By far, most of them are metals. In fact, there are very few non-metals. And the non-metals are colored this blue color, this sort of powdered blue color. And again, you can see there are very few non-metals, and they lie on the right side of the periodic table, whereas the metals lie on the left side of the periodic table over here. Okay, now in between, you're probably realizing that there's another tsatsi group here called the metalloids. Sometimes those are called the semi-metals, and those elements have the characteristics of both metals and non-metals, or metals or a non-metal, depending on the situation. I want to point out something else, which is these two periods that are shown here on the bottom. This one here is called the lanthanides, and this one down here is called the actinides. Okay, the lanthanides and the actinides. And the reason that the lanthanides and actinides are put down here is because you can see that cerium, element number 58, should follow element number 57. The reason why is because if they were inserted in here, it would just make the periodic table too wide. You're like, is that the reason? Yes, that's the reason. In fact, if you Google periodic table with lanthanides and actinides inserted, it'll come up right away and it'll show you what it looks like. It's just a little bit longer. Okay. Anyhow, let's talk about, I'm going to skip this part about the chemistry in action. You can read that on your own time. and I want to get right into molecules. People talk about molecules all the time. A molecule is an aggregate of two or more atoms in a definite arrangement held together by chemical forces. A diatomic molecule contains only two atoms. Now, there are 1, 2, 3, 4, 5, 6, 7 diatomic elements, and they are all highlighted right here. These are the diatomic elements. And what that means is that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, all of those elements, when they exist pure, when they're found pure, okay, hydrogen gas, for example, does not exist as just H. It's H2, which is shown here. Nitrogen gas does not exist as just N. It's going to be N2. Same thing with oxygen. It's O2. There's a big mistake here. This should not be BR. Let me cross that out. It should say BR, lowercase 2. I don't know what the heck is. Oh, that's not listing all the diatomic molecules. Hold on. Sorry, there's a mistake here. Anyhow, hydrochloric or hydrogen chloride and carbon monoxide, these are also molecules. Let me just finish what I was saying about the diatomic molecules, because I want you to have them all down pat. You must memorize these. A lot of students like this one, which is, I don't even use it. It's Brinkol, Hoff. Okay, so it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. I got something even better for you. Are you ready for this? Have no fear of ice cold beer. Okay, that's how I remember them. But either way, works perfectly fine with me. So the diatomic molecules, you have to be aware of those, or the diatomic elements. Sorry, a diatomic molecule. Okay, so that's what my point was. Sorry, Mr. Dio is kind of confused here a little bit. So a diatomic molecule is a molecule that contains only two atoms. So the diatomic elements are examples of diatomic molecules. So let me erase this here, and I should put here. These are the diatomic elements, and you must memorize those. Okay. A diatomic molecule is any molecule that has only two atoms. Examples are H2, N2, O2, Br2, HCl, carbon monoxide. We could go on from there. Okay, H2O is a diatomic molecule, right? No, sorry, H2O is not a diatomic molecule. Jeepers, I'm getting tired. Anyhow, a polyatomic molecule is one that contains more than two atoms. Let me think of another example of a diatomic molecule. I don't know, I2 would be considered a diatomic molecule. Anyhow, a polyatomic molecule contains more than two atoms. Examples are O3, H2O, NH3, CH4. Hey, let's do a little trivia here. Can anybody tell me what O3 is? Just curious if anybody knows. You don't have to know it immediately, but there's a common name for it. Yeah, Chris says ozone. That's right. You've all heard of the ozone layer. So ozone is O3. H2O, I know you know what that is. That's water. Does anybody know what NH3 is? Or CH4? No? Okay, I'll help you out then. NH3 is ammonia. And CH4 is methane. Okay? It would be wise to memorize these common names. And if you're like, just those ones, just these four, yes, those four. Okay? So make sure you know all the diatomic elements, and make sure you know these polyatomic molecules, the ones that I have highlighted in yellow here, because, and if you're like, why just those four? Because those four come up quite a bit in this class. Okay? All right. Who's tired? Just me? Okay, we got 13 minutes left. That means we cover all kinds of fun stuff. All right. So if we were in class, I'd ask you, if we were face-to-face, I'd ask you if you'd heard of an ion. But an ion is simply an atom or a group of atoms that has a net positive or negative charge. So some kind of charge. And of course, I'm sure you're all perfectly aware that there are two types of charges, positive and negative charges. And so if an atom or a group of atoms has a positive charge, we call that a cation. I think it's easy to remember because you do cat ion, right? And the letter T kind of looks like a positive charge. An anion, on the other hand, has a negative charge. And I think that's easy to remember, right? Anion. And you kind of have the anarchy symbol there, right? Remember a negative charge. Anyhow, let's look at this in a little bit more detail. So a cation, it says if a neutral atom, like sodium, if you look at sodium on the periodic table, you see that it's element number 11. Remember, the atomic number is the number of protons. So that means that sodium, when it's neutral, when you just have pure sodium metal, it has 11 protons and 11 electrons. What would happen if it lost an electron, right? That brings back the old chemistry joke. A sodium and a potassium walk into a bar. The sodium loses an electron, and he says, I think I've lost an electron. And the potassium says, are you sure? And he says, I'm positive, right? If you lose, think about it. If you lose negativity from your everyday life, what are you becoming? More positive. So electrons can be lost because, again, I'm repeating this for probably the 6th time tonight, that what governs the identity of an atom is the number of protons, which did not change. So again, if sodium loses an electron, it goes from 11, 10, it's going to become positive, right? What about a chlorine? If you look at chlorine on the periodic table, it's a halogen. It has 17 protons, 17 electrons. That's when you just have pure chlorine, okay? Or chlorine that's uncharged, I should say. If chlorine was to gain an electron, electrons are negative. So if it gains an electron, right, if it goes from 17 to 18, it's going to become negative. Give me a thumbs up if you follow me on that. Loss of an electron becoming positive and gaining an electron becoming negative. All I see is ha-ha from Chris about my, okay, good. All right, great. So we've got cations and anions. We got chemistry students on the line here, so let's keep talking. Okay, just a little bit more definitions. A monatomic ion, it's not monoatomic, it's monatomic. A monatomic ion is some kind of ion that only has one atom, okay? So here we have a sodium cation, right? This is a sodium cation. We have a chlorine anion. It's actually called a chloride, but I'll talk about that later. We have a calcium cation. We have an oxygen anion. That's called an oxide. Again, more on that later. You have aluminum cation and nitrogen anion, and that's called nitride. And again, more on that later. Now, the polyatomic ions, woo, you're going to have to memorize the polyatomic ions, and that is always tough for students. It doesn't mean it's impossible. Many people have taken this class before you, and many people will take it after. I'm just telling you the reality that memorizing the polyatomic ions, and there are a lot of them, is a lot of work. No two ways about it. Okay, so you see we have OH here. I can even help you out. This is called a hydroxide. This one here is called a cyanide. This one is an ammonium, and this one here is a nitrate. And so you're going to have those and several others memorized. You hear in this slide, you see some common ions just shown on the periodic table. So you kind of notice some trends here. If you look at the metals, right, all these things here in green, these are all metals, okay? You notice that they only have positive charges. That's kind of interesting. So that tells you right away that metals like to form cations. So metals like to lose electrons, right? That's a conclusion we can draw right away. Another thing I want to point out is that if you look at the elements in group 1A, look at this. They all form the same charge, right? Didn't we say that people in the same family are similar, right? They have similar characteristics. I did. So look, you have lithium plus one, look, lithium plus one, sodium plus one, potassium plus one, rubidium plus one, cesium plus one. Look at the elements in group 2A. Hey, they're kind of similar too. I'll have to use the yellow again. 2 plus, 2 plus, 2 plus, 2 plus. In here, you see how the periodic table kind of sinks down here a little bit? We call these metals here, we call these transition metals. Transition metals. Okay, transition metals, you see that they're special. They can adopt more than one charge. For example, if you look at iron, which has the atomic symbol Fe, it can be +2 or +3. Look at nickel, it can be +2 or +3. Look at copper, it can be +1 or +2. Now you're going to have to know those, but before we get into that in even more detail, look at these three here: zinc, cadmium, and silver. These are 3 exceptions. And you might be wondering, Mr. Dion, why are you harping on about exceptions? Well, because I've looked at the ACS study guide enough to know that they expect you to know these 3 exceptions that I've just highlighted here. These transition metals, zinc, cadmium, and silver, can only have one charge. What else? If we go over to the non-metals side of the periodic table, so over here, this is kind of interesting. You see that not only do the anions in the same group all form the same charge. So look, you have nitrogen has a -3 charge, and phosphorus has a -3 charge. Oxygen has a -2, sulfur is a -2, selenium is a -2, tellurium is a -2. And look at all the halogens. They all like to adopt a -1 charge. So again, the halogens, or sorry, any nonmetals, they like to gain electrons. So metals like to lose electrons, nonmetals like to gain electrons. Okay? Let me point out one more thing that comes to my mind before we move on. Any element that's not a transition metal, we call those main group elements. So I'm going to let you write that down on your own, a main group element, but that's something that you should know as well. But in the interest of time, I'm going to skip ahead here and get into formulas and models. And we have several different ways that we can represent molecules. We can either use what is called molecular formulas, which is just using atomic symbols and subscripts. We can use a structural formula. I really love these. There's actually an even better name for these. These are what we call Lewis structures, and we will look at those in gross and dirty detail later on in this class. We have ball and stick models, and we have space filling models. And both of those are used to help us understand the geometry or the shape of molecules, and to help us understand the relative sizes of atoms and molecules sometimes with those space filling models. Anyhow, let's get back to formulas here for a second. So we can have what's called a molecular formula or an empirical formula. Let me show you the difference, and you have to know these. A molecular formula shows the exact number of atoms of each element in the smallest unit of the substance. An empirical formula shows the simplest whole number ratio of the atoms in the substance. So they have some terms in common here, right? Whole number, right? But the difference is that in an empirical formula, it's the simplest whole number ratio. Well, let me show you an example. If you look at the molecular formula of water, H2O, there's no way I can simplify that down to any lower whole number ratios. And so my empirical formula is still going to be H2O. If I look at glucose, which is C6H12O6, if I divide that whole thing, if I divide all of that by 6, I end up with the simplest possible whole number ratio, which is CH2O. And you can see, and you don't need to know this, but you can see that for the one carbon atom, there's a water molecule, and that's why we call them carbohydrates. Anyhow, I digress. If you have ozone, its molecular formula is O3. It does have an empirical formula. It's just O, right? Because if I divided that by 3. This next one here, N2H4, that's called hydrazine, and you can simplify that by dividing the whole thing by 2. So give me a thumbs up if you follow me on the difference between empirical and molecular formula. Not meant to be a mind-boggling concept, but you have to know the difference between the two. All right, great. Thanks, Tyler. With that in mind, it says here, write the molecular formula of methylamine, an organic solvent, from its ball and stick model shown below. Methylamine, I think, is also the amine that is responsible for what's known as fish odor disease, which is where some people can't metabolize ammonia properly. All right. Brittany says, I thought O couldn't be just O, but has to be O2. We're not talking about a molecule. We're just talking about an empirical formula. When oxygen exists in its pure form, it has two possibilities. It can either be O2 as a diatomic element, or it can be O3, which is ozone. All right, so you can see that the gray elements here, or the gray spheres, those are hydrogens. The black one is carbon, and the purple one is nitrogen. And so we have 5 hydrogens, right? We have H, we have hydrogens, we have 5 of those, we have carbons, we have 1 of those, and nitrogens, we have 1 of those. And so if I put all that together, I would get CH5N. Now you're just learning chemistry right now, and so if you had written H5NC, I'd still grade it correct. Okay, you're learning about how to write down formulas, but that would be the molecular formula for this compound right here, which, by the way, is a very stinky compound. Okay. Well, it's 6:48. We're getting pretty down the wire here. So if you can just bear with me for a second, I just want to show you where we're going. We're going to talk about ionic compounds, reactive elements. We're going to talk about how metals like to lose electrons and non-metals like to gain electrons, and that is why they react together to make ionic compounds. We'll go over all of that. And then right here, so we're only 2 slides away from chemical nomenclature, okay? Look, I know that all of you are investing your time, your energy, probably your money to take this course, and I want you to protect your investment. I want you to be successful. Look, I don't want to come off sounding like a dad. In fact, I should stop recording right now. Why don't I do that? Okay, I'm going to stop recording. Stop.